This video will give a short overview of geothermal energy. We will discuss the potential of two different geothermal sources, the heat generated from magma and subduction zones. Magma has a lot of potential to be a very effective geothermal source. The heat it generates can vary in temperature from 700 to 1300 degrees Celsius. Currently, there are several magma hotspots around the world, including Iceland and Hawaii. It has been estimated that a magma well that can produce a dry steam of 400 degrees Celsius can generate up to 25 megawatts of electricity. This can power up to 30,000 homes. The second geothermal source is subduction zones. They are located at the edge of tectonic plates and occur when one plate is pulled beneath another. The major subduction zones currently circle the Pacific Ocean, forming the well-known Ring of Fire. Areas near subduction zones have a potential for reservoir temperatures ranging from 175 to 345 degrees Celsius, which can then produce 0.1 to 715 megawatts of electricity. There are three main types of power plants used to extract energy from geothermal sources. The first type of power plant is called a dry steam power plant. This plant uses naturally occurring steam from a reservoir to drive steam turbines. The second type of power plant is called a flash steam power plant. These plants take high pressure and temperature water from the earth and convert it to steam to run their turbines. There are two different types of flash steam power plants, single flash and double flash. Single flash power plants use a single flash tank to create the steam, while double flash plants use two tanks. Double flash plants are more efficient. Single flash plants are very similar to dry steam plants and can be converted easily when the source begins to dry out. The third type of power plant is a binary cycle plant. These plants use hot water from the earth to vaporize a separate working fluid to drive turbines. Binary cycle plants are typically used with low enthalpy sources and can extract energy from a source as cold as 73 degrees Celsius. The efficiency of a geothermal plant depends on the enthalpy of the fluid in the geothermal reservoir as well as the type of plant used. Binary plants are used for sources with low enthalpies and have an efficiency of 3 to 9%. Single flash and dry steam plants have very similar efficiencies, between 6 and 18%. They are used for sources with high enthalpies. Double flash plants have a narrow range of enthalpies that they are useful for, but are generally more efficient than single flash plants operated with equivalent sources. They typically have an efficiency of 5 to 15%. The average geothermal power plant has an efficiency of 12%. This is much lower than other power plants, which range from 32% for nuclear to 40% for natural gas. Now we'll turn to the exploration process. Exploration and drilling accounts for about 42% of overall geothermal project costs. We can generalize this process into three distinct phases. The first of these phases is regional reconnaissance and land evaluation, where a broad research for the geothermal sources is conducted. Remote sensing methods are very popular to use in this phase. Remote sensing techniques use the reflection of various wavelengths of radiation to get detailed estimates of the topology and geomorphology of a region. Two remote sensing methods are commonly used for geologic purposes. The first is hyperspectral imaging. This can be used to identify geological materials and heat flows. The second technique is light detection and ranging, or LiDAR. It is good for generating topological information. The cost of these options is proportional to the amount of data they provide. The next phase of the exploration process is geothermal appraisal, where short-range geothermal information about a region is acquired. Geophysical techniques are commonly used for this stage. The most common geophysical techniques are seismology and magnetotelluric surveys. Seismology uses acoustics to map changes in density, while magnetotellurics uses electrical pulses to map changes in conductivity. Both of these properties can be correlated to pockets of hot fluid or metamorphic rock, which have high geothermal potential. Comparing the cost of these survey options, seismology is more expensive than magnetotellurics because it requires more equipment and the surveys are typically done over a larger area. However, seismologic surveys are popular due to the use in oil and gas industry. It is important to note that these techniques are typically used together because they compensate for each other's weaknesses. The last phase is exploratory drilling. Slim hole drilling is a hollow drill technique, meaning that the drill bit is used to extract cores of rock for geologic analysis. Slim holes are typically drilled to a maximum of 2.5 kilometers. They also require a rigid and well-supported drilling structure in order to penetrate to these depths. Thermal gradient holes are also narrow but are drilled to shallower depths, around 1.2 kilometers at maximum. This means that they can be drilled more quickly and only require a truck-mounted rig. The temperature gradient of these holes is measured to gauge the thermal potential of the location. Hydrologic data about the region can also be generated if many holes are drilled. When looking at the cost of these two techniques, one can see that the slim hole technique is more expensive when normalized to depth. This reflects the higher equipment and infrastructure costs of slim hole drilling. In light of all this, two salient points about geothermal energy should be made. The exploration process constitutes most of the cost and time. This is tied to the uncertainty of the resource and its dependence on location. As well, its thermal efficiency is much lower than other technologies.